polynomials and rates of change. Today we're going to get out of that long process of doing the limit of the difference quotient. In math, a lot of times we start by learning the long way of doing something to gain an understanding of what it really means. A good example is when you first learned to graph a line, you probably did an XY chart. You didn't know anything about the y equals mx plus b as a shortcut. You did an XY chart, picked several points. Your teacher probably had you do 3 or 5 different x values, and then you plugged that into the function. You got a y value, and then you plotted the points, and they became points in a straight line. So you graphed that line, and over time, you learned that if you put it in the form y equals mx plus b, you can do a shortcut and just put the b on the y-intercept and mark off the slope, and you're done. Well, in the same sense here, we learned the meaning of what all that had to do with the graph and how that relates to the limit of the difference quotient, the slope of the tangent line. Today we're going to take a little shortcut. We no longer have to do that process. So let's start with theorem 2.2, the constant rule. The derivative of a constant is what? Well, think of this part in the green here. What is the slope of the line y equals 3? That's obviously going to be 0. So the derivative of any constant, think of it in terms of the slope of a constant function. The slope is going to be 0. In notation, the way we write that is the derivative of a constant with respect to x is 0. For the power rule, this is the one that we will use quite often. It's the most basic of the differentiation rules that we use regularly. This one says, if n is rational, then f of x equals x to the nth is differentiable. So we have a polynomial. That means it is differentiable. Think of any polynomial you've ever seen. It's a smooth curve. It does have a tangent line that has a slope we can get. And the rule is, if you start with x to the nth, then f prime of x, the derivative of that, is n times x to the n minus 1. So take a look at this form. What you're going to do is you're going to take this exponent, put it in front right here, and then subtract 1 from the exponent. So it becomes n comes in front, and n minus 1 stays up top. So in the different forms we're going to see, it often helps to rewrite the function in the form x to the nth. So for example, if we have in the black here, f of x equals x to the 5th, take the 5, put it in front here, then subtract 1 from this, so your answer for the derivative is 5x to the 4th. It's that easy, okay? Now, how can we take this expression and write it in the form x to the nth? Well, we're going to make x to the square root of x, write that as x to the 1/2. And so as an intermediate step, take this 1/2, put it in front, subtract 1 from here, and so your next step is going to be h prime is 1/2 times x to the negative 1/2, but we're not going to leave negative exponents in this class, so we're going to change that to 1 over 2 times root x. Guys, this function right here, the square root of x, is a very common one. You probably want to memorize that its derivative is 1 over 2 root x. When you get something in bottom, you can change it to a negative exponent to do this rule, and then change it back out of a negative exponent. So this would be x to the negative 4th. There we go. X to the negative 4th. Now let's follow the same rule. The negative 4 comes in front. Subtract 1 from here. Be careful. The negative 4 minus 1 is negative 5. So you get this look here, and then rewrite it in a form that's acceptable. We don't allow negative exponents, so negative 4 over, so y prime equals negative 4 over x to the 5th. Y equals x, think of that as x to the 1st power. Well, it still follows the same rule. Put the 1 in front, drop this to the next integer down, so 1 minus 1 gives you 1 times x to the 0, and all of this is just 1. So we say that if y equals x, then dy dx equals 1. In other words, what's the slope of y equals x? The slope is just 1. So the constant multiple rule, if f is differentiable and c is a real number, then c times f is differentiable, and the derivative of c times f is c times f prime. So what that means is, if you have, instead of just 1 over x right here, what if we have negative 3 over x? Well, think of that negative 3, just leave it in front and apply the same rule that you just did above. Forget about this negative 3 when you're differentiating, and now let's differentiate this thing here. That's what this says up here, is we can, if we have the derivative of c times a function, the c just stays in front, and we differentiate the function. So the negative 3 stays in front right here. Okay, and then we're going to follow that rule that we just said. We're going to focus on this part. Take the negative 1, move it in front, and drop that by 1. So the negative 1 comes in front, times x to the negative 2, and then we clean it all up and put it in an appropriate form. This guy right here is a little bit ugly, but he's not too bad. How can we rewrite this in this form? Well, think of it as a 1/2 in front as a constant, right? That would be this thing right here is the 1/2. And all of this part would be x to the what? X to the negative 2/3. So when we rewrite it first, you're going to have 1/2 times x to the negative 2/3. Now we're going to leave this 1/2 in front, forget about it, and now just differentiate this part. So the negative 2/3 that comes in front, and then we subtract 1 from the exponent, so we get this. And now we clean it up and see what else needs to happen. So the 2's cancel out, and the negative exponent goes to the bottom, and you can rewrite it with radical form or rational exponents. Either way right here is acceptable. Okay. Your assignment today will walk you through this process and ask you to take a function. First, we'll put it in an appropriate form so it looks like x to the nth, then differentiate so you get a form just like this, and then rewrite it to simplify just like that. So it's kind of a 3-step process. You go first rewrite it, then you differentiate, then you clean it up. All right. The theorem 2.5, the sum and difference rules. The derivative of the sum of difference of two functions is the sum or difference of the derivative. So if you have 2 terms to differentiate, then just differentiate each one separately. So for example, down here in the very bottom, we have x to the 4th minus 3x cubed plus 7x squared minus 2x plus 5. Differentiate each term separately. The first one becomes 4x cubed. The next one becomes what? Negative 9x squared. The next one becomes 14x. The next one becomes, be careful, the negative 2 stays in front. That's x to the 1. It comes in front. The slope of a negative 2x is just negative 2. So this just becomes minus 2. And what is the slope of 5? The slope of 0, or the slope of 5 is 0. The derivative of a constant is 0. So this in the black is f prime.
All right. So if you turn the page, I'm going to pick up where those notes left off here. So a couple more examples to go through. These first two are, again, really just putting them into a proper format, like a more friendlier format, so you can do the power rule to differentiate. So on this one, we're just distributing the x squared. So if you distribute the x squared, it's going to look something like this. Now you can go ahead and use that power rule. So again, think of this as x to the first. So we're multiplying your 1 to the front. This becomes x to the 0. So you're just left with a 1 right there. Same thing with your second term. Multiply that 5 to the front. Drop your exponent down to a 4, and that's it. You got your derivative. So on these ones, there's a couple different ways you could approach these. Probably the easiest is just to bring that x squared up to the top and call it x to the negative second, and then you can distribute it. Remember, when you distribute, you got to add those exponents together, and you should get this look right here. And now this is in a way better format for differentiating. So now you can use that power rule on each term. Be careful with those negative exponents. Remember, when you are subtracting 1, make sure that that works out the way it's supposed to. And so that one would work out all the way to here. So real common examples that you're going to run into are ones like this, where you are now finding the equation of a tangent line. So for these, the general idea is I just need a point and a slope, so I can plug it into my point-slope formula. And they're going to give this to you in sort of different ways. This problem, they just tell you what the point is. So here's my x1 and y1. And so our slope is going to come, of course, from the derivative. So that's the whole point of doing derivatives, is to get a slope function. So if we clean this guy up a little bit, put it into a friendlier form. So if we expand our binomial here, it's going to look like this. Distribute that 2. And now when you differentiate it, you get this nice simple derivative function right here. So keep in mind that whenever you are looking for a slope within a derivative function, all you have to do is plug in the x coordinate, right? And so they could have just given us this to start with, right? And so we could have just plugged in that negative 4 right here for x, and that gives us our slope of negative 20. If they didn't tell us that the y coordinate was 50, we could have just plugged our negative 4 into this original function to come up with this y coordinate that goes with it. But once you have your x, your y, and your slope, we can just plug that into point slope, which looks like this. And always best to sort of put that into a slope intercept form. So this is really the best format to leave those in. On this guy here, this is our last example. So keep in mind what an x to the 4th graph would look like, right? Remember, those take on sort of a W shape typically for most x to the 4th type graphs. So if we were looking for a horizontal tangent line, keep in mind that horizontal lines have a slope of 0. So something we've looked at earlier on this year is this whole piece of the graph right here would have a negative slope, right? So anywhere I draw a tangent line on this piece of the graph, I'm going to have a negative slope, and then it transitions right here into a positive slope, right? Well, what do you have to cross over from negative to positive, right? You have to pass over 0 for that to happen. So right here, anytime you see a local minimum like this, or a local maximum like this, you're looking at a 0 slope or a horizontal tangent line at those points, right? So I should have a horizontal tangent line here, here, and here. So there should be 3 of these. So if we take this guy and use our power rule to get the derivative function, it's going to look like this. Because our slope is 0, I can set my derivative equal to 0 and then solve for the x coordinates, right? And so if you solve that equation for x, you come away with those 3 x values. And so that would make sense now with the graph that we're looking at, right? So at -1, where x is -1, where x is 0, and where x is +1, we're going to see those horizontal tangent lines. And then one last one you can peek at down here. This was just sort of a side note on this one. This was just sort of a notation thing. So here's the function 3x squared. So if we get the derivative, it's going to be 6x using our power rule. So if I want the slope where x is 2, all I have to do now is plug in that 2 into my derivative, and I get my slope of 12. This is just a way of writing that to show that you are plugging in 2 for x into the derivative and getting the slope at that point. So that's it for part 1.